Welcome to section 2.5, and here we're going to discuss the determinant of a matrix. So the idea is to determine if a matrix uh, is invertible without actually finding the inverse of the matrix. Right. So consider a system of equations: ax plus by is equal to e, and cx plus dy is equal to f, and assume that a and c are both not equal to 0. So if we multiply the first equation by c and then the second equation by a, we get this system: acx plus bcy is equal to ec, and then acx plus ady is equal to af. Now if we subtract the first equation from the second, we see that we say acx minus acx, we get a 0. Then we say ady minus bcy, we get ady minus bcy. And then if we factor out the y, we get ad minus bcy, right? And then here we say af minus ec. So now from what we already know, this system is going to be unique. Sorry, this system has a unique solution if and only if AD minus BC is not equal to 0. Because if it's equal to 0, then either we have got an infinite number of solutions, or we have a no solution depending on what will be the value here. So the only way we get a unique solution is when the coefficient here is not equal to 0. Right? And that is what we call the determinant of the coefficient matrix A, B, C, D. So if you look at this original system, the coefficient matrix would have been A, B, C, D. Right? So the determinant of A, B, C, D becomes AD minus BC. So it determines whether this system is going to have an inverse or not, just by looking at this value here. If it's 0, then we know we are going to have we don't have an inverse. If it's not equal to 0, then we have an inverse. Right. Uh, let's look at definition 2.5.1. So we are just formalizing what we have done. The determinant of a 2 by 2 matrix A, which is equal to aij, is denoted by DETA, which is equal to A11, the first entry, times A22 minus A12 times A21. Right, so that's how we find the determinant. So for example, if we look at example 2.5, the 2.5.2, where A is equal to 1, 2, 3, 4, then the determinant becomes 1 times 4 minus 2 times 3, which is 4 minus 6, which is 2. Right. Now the determinant of a 3 by 3 matrix AIJ. So if we were to do the same thing that we did but with 3 variables, it will be a bit more complicated, but we'll get to a stage where we can say the determinant is equal to, so this value would determine if we have a unique solution or not. So this would be this is not equal to 0. If this is not equal to 0, then we'll get a unique solution. So we can say the determinant of A is equal to A11, the determinant of this matrix, minus A12 times the determinant of this matrix, plus A13 times the determinant of that matrix. We are going to have a way of remembering all this information later when we look at a general determinant of a matrix. So for example, if we look at A, which is this 3 by 3 matrix, we will see that we've got 1. So we've got 1 times 5 6 5 6 minus 8 9, and then minus 2, so the minus there, and then the 2 is the entry here, and then we have um, this is supposed to be minus 2, so that's minus 2 9, and then 6 7, and then plus 3, so the 3 is that one, and then we can say minus 2 8, and then 5 7. I think this one is the one that's supposed to be minus 4. Right, so if we do the evaluation, we can then calculate and see that the determinant is 240. You can do that. It's easy arithmetic. Right, so for us to be able to determine or to define a determinant of a general n by n matrix, we need more definitions, or at least we need one more definition, which is definition 2.5.5. And it says if A is Aij, if Aij is a square matrix, then the matrix that we call A, so it's capital Aij without any brackets to differentiate it from that, is the matrix obtained after deleting row I and column J from A. So whatever is here, you delete the ith row and then the jth column, and then so that is the matrix, and then the minor entry Aij is the entry in row I and column J of A, of the original, right? Is determinant of this new matrix after deleting row I and column J, and is denoted by Mij, right? So we're going to, this value is going to be important. I think we have looked at it before already when we were calculating here, but we'll see it when we look at a more general case, right? So if you look at this, if A is an n by 1 n plus 1 by n plus 1 matrix, then Aij is equal to is an n by n matrix, and this is simply because we remove one row, so we end up with n rows. We remove one column, so we end up with n columns, right? Example 2.5.7. If you have a matrix 1 2 3 4 minus 5 6 7 minus 8 9, then A21, so A21 would be so what is where would the entry be? So okay, so what we are just saying is we're going to remove the second column, and then the first, sorry, we're going to remove the second row and then the first column. So what we are left with is 2 9 in on the diagonal, and then 3 minus 8, so 2 3 minus 8 9, which is what we have there, right? And then M21, so the minor becomes um, becomes the determinant of this matrix, and that's just 18 plus 24, so 18 minus 24, which is 18 plus 24, which is 42, right? Now let's look at the definition of the matrix the definition of a determinant of an n by n matrix where n is greater or equal to 4. Then the determinant is going to be equal to, this will be corrected, this is supposed to be coming here, so we'll correct it in the slides that will be posted, right? So determinant A is equal to the summation from j is equal to 1 of minus 1 times 1 plus j of a1j times m1j. So what is it saying? It's telling us that we are going to be considering values in the first row. If you look at a11, a12 up to a1n, so we are going that, and then we are also considering the m21. So we know a21, a11, so we can calculate m21 and so forth. So that is the formula for us to find the determinant of a matrix where n is greater or equal to 4. Right, so we are going to look at an example, which is example 2.5.9 in the textbook, and that is the matrix. And so therefore, what is the determinant of A? The determinant of A is going to be A11. So we're going to say minus 1 squared, because if we look here, we are starting from j is equal to 1 up to j is equal to n, right? So we are going to say minus 1 squared. So minus 1 squared times, what is A11? It is 0 times M11. So M11, well, so in this case, because this is 0, we don't really need to calculate M11 because it's just a waste of our time. We are going to get it multiplied by 0, so we don't worry about that. And then the second entry from that will be minus 1 cubed. So minus 1 cubed times, what is the A12 entry? It is minus 1. So minus 1 times minus 1 cubed times M12, right? Plus 2. So the 2 here is this entry 2 times minus 1 to the 4, and then M13, right? And then times minus plus minus 1, this minus 1 times minus 1 to the 5, and then M14, right? So we need to find we don't need to find M11, but we need to find M12, M13, and M14. M12, what is it? So if we go back, so 1, 2, so we are talking of this. So if we remove this column and then this row, we are left with 1, 1, 2, 3 minus 2, 1, 1, 2, 2, right? And then, so that's what we have there. It's actually 1, 2, 1, the last one, right? So we have that. And then we can find the determinant of this, and then it's just arithmetic. It's not too difficult. It takes a bit of time, but it's not too difficult. We see that it's 10. If we go to M13, so we are on 13, so we are here. So if we remove that and that, we get 102, 3 minus 1, 1, 101, right? Which is what we have there. And then you can find the determinant, and then you get M13. And in this case, it's 1. And then for M14, we do the same. We remove the first row and then the fourth column, and then we are left with this matrix here, and that is what we have there. And then you can find the determinant, and it turns out it's equal to minus 1. So basically what we have is determinant of A is equal to M12 plus 2 times M13 plus M14, and we know all these values, and the determinant is 11, right? So we managed to find the determinant of the matrix. So in this case, you notice that we were working with the first row, but actually we don't really need to work with the first row. Actually, it turns out that we can actually work with any row or any column for that matter to find the determinant, and that is the next theorem that we have. And it says let A be an n by n matrix Then for every I, and in this case I represents row, so for any row that you pick, the determinant of A will be equal to, so you see the I is fixed here, so the I doesn't change. What is changing is just the column. So it means that we are working with a fixed row. So for any row that you pick, this will be the formula, right? It's pretty much the same formula, except instead of having a 1 here, it has an I, right? And then for any row, so here we are saying for any row, so for any column, again, we have that formula. And in this case, you will notice that the J, the column is fixed. What is changing is the row, the value for the row, 1, 1, 2, 2 there, and n there, right? And so that means that when you're calculating the determinant of a matrix, you can use either a row or a column, uh, well, whichever is convenient will work. So let's look at the proof. So the proof is a special case of a special case, and that's all we are going to do. The general case would take us forever, but anyway, we are going to look at the special case of it. So we are, this first special case is we are looking at a 3 by 3 matrix, and then we are going to look at just one row, and then that's what we have. So so what we want is to prove that 2.7 uh, will give us a determinant, basically. So and then we are going to look at the second row, right? And then just show that that will still give us the same value. So according to definition 2.5.3, which is the definition of the determinant of a general matrix, of a general n by n matrix, says determinant of A will be equal. So here here we are using the first row, right? The traditional the first definition that we got, which talks about the row, and so that becomes the expansion of using the first row. And then if you calculate the determinants of these, you find out that that is equal to that, right? Now on the other hand, we're now using the fact that here now we are using the second row. So we are summing from j is equal to 1 up to 3. So here, because we are dealing with n 3 by 3 matrices, our n is equal to 3. And then we use the formula minus 1 to the 2 plus j. So the 2 here is representing the row, right? And then if we do the expansion, we get that, right? From there, we can then calculate the determinants of these, the determinants of those, and then we have something like this. So if we expand it and then rearrange it, we'll see that we get to this stage. So this was supposed to be 2.10. 2.10 is here now. So you see that this is just the same as that. When we calculate the determinant there, we found out that it will get to this, and that is equal to that. So we use the column, we found the same value, and so therefore the determinant of A becomes equal to that when we are using the second the second row. So therefore that is true, but it's true in general, really. We just proved a special case, right? So let A be an n by n matrix. For any row, the expression that is called the expansion of the determinant of A according to row I, right? And here it's supposed to be J. So for for any J that you pick, the expression determinant of that, now where the J is fixed, is called the expansion of the determinant of A according to column J. So really you can just pick whichever row or whichever column is convenient. So we are going to look at another example, and we are going to use two different expansions to just show that to just illustrate the point that we can use any row, we can use any column. So according to example 2.5.9, so we've looked at this example previously and we saw that the determinant is 11. So we are going to expand this determinant according to the second column. Right. So determinant of A is equal to that expansion from I is equal to 1. So here we are, so you see this 2 is representing the column and it's fixed. That's what we are expanding according to. So therefore we have that, and then we can calculate determinant of M12, determinant of M22, M32, M42, and because we are using the second column, you will see that we've got two zeros, so that makes life easy because now we just need to calculate two determinants of these 3 by 3 matrices, M12 and I think M32. Those two, the rest are the other two are zeros, so that helps with the calculations. And then if we do that, we get the same value 11. So you can just verify the calculations if they're okay. And then if we do for the next example, we are going to do an example 2.5.13, where we are going to show that we can do an expansion according to the first column and according to the second row, and we still get the same solution. So if we expand the determinant according to the first column, we get, so you see that the first column, the one here is not changing, so 1 1 1 1, everything is 1 here, so because we are expanding according to the first column. So we can find M12, M21, M31 like that. And I think there's a step that was skipped here. Anyway, so we get that, and then it's just arithmetic routine calculations that you get. And if we expand using row 2, so the 2 here is fixed, again it's just arithmetic. I think there's some steps left, you can do the calculations, and you find out that we still get the same value 1. There we got 1, and there we got 1. So really it's just an illustration that expanding according to whichever row or whichever column works. Thank you.